Thank you, Pierre and Henry. It's a great honor, and it's very nice of you to introduce me so nicely. Let me connect my laptop. It's a great honor for me to be the first recipient of the Pat Joe Yzurdiaga Chair in Experimental Science. And I'll give a little bit of an overview of the research we've done. This is my work that I'm behind on. You don't have to look at that. I'll give an overview of the Higgs discovery and where we stand now. But mostly I want to talk a little bit, at least at the end, I want to talk a little bit about what comes next. So this is a picture actually of the experiment now. We've actually opened it up. It's been pulled open, and we're doing lots of repairs. But we ran for 3 years, and in that time collected lots of data and had some spectacular results. So by way of introduction, I just want to tell you a little bit about particle physics. We have something we call the Standard Model, and this is like a new periodic table of the elements, if you like. It took about 100 years or more for advances in theoretical physics and lots of discoveries in particle physics to put this model together. And it's a very simple model. If you look, we're down to, let's see if I have a pointer here. There was a famous physicist once who just threw that was back when they had plastic transparencies, and he took basically the same thing and he threw it on an overhead projector, and he said, after 100 years and billions of dollars, this is all we know. But actually, it's a good thing. We've reduced the basic building blocks of matter to these particles. There are fermions, spin-and-a-half particles, that are quarks that have strong interactions, and there are leptons, which have weak interactions. The charged ones also have electromagnetic interactions, and these are the force carriers. They're bosons, particles with spin 1. Now, there was one piece that was missing, and that was the Higgs. Okay? But putting this model together was really one of the greatest achievements of 20th century science. Now, there is a problem, or a potential problem, with the Standard Model and the Higgs involvement in it, and that's the Higgs mass. It turns out that in quantum field theory, if you were to try to calculate the mass of the Higgs, all of the Standard Model particles tend to want to contribute a huge amount. In fact, they try to contribute an amount that's up to 10 to the 19th times the proton mass. And we know the Higgs can't be that heavy. In fact, we've detected it in a much lower mass. So this is a problem. And so the question we have is, well, there's two ways to solve this problem. One is that the universe is extremely, extremely finely balanced to a level that's, we find, a little bit hard to believe. And we call this fine-tuning. And everything would work out, but things would have to be correctly balanced. Parameters would have to be known and set to 30 decimal places or something like this. Or there may be something that provides a natural balance that solves this problem. And in fact, one thing that will do that is if there are partner particles to all of the particles we know, partners that we haven't seen yet, these partner particles could cancel out the effects of the Standard Model particles and leave us with a Higgs mass that's reasonable. So the question would be, how do you get these partner particles? And the most compelling way is to invoke a symmetry transformation that connects each known particle to a new one that is very much, but not exactly like it. And this we call supersymmetry in most cases. And we think this is the natural choice. Okay, so this is what you get when you extend the Standard Model, introducing this new symmetry. For every spin-and-a-half particle, you get a spin 1, or spin for every fermion, you get a boson. And we would have essentially like a copy of all of the Standard Model particles, but with slightly different properties. And there'd be some conservation characteristics as well. There are interesting impacts of this. For one thing, when you just have the Standard Model and you look at all of the strengths of the different forces, the strong, weak nuclear force and the electromagnetic force, we don't study gravity directly because it's too weak. You find that as you go back in time to higher and higher energies, you see that these coupling strengths, the strengths of these different forces, actually tend to come close to each other, but they don't quite converge. But if you introduce supersymmetry, they actually do converge. very well. And this seems like it can't be an accident. So it unifies all the strengths of all the forces at about 10 to the 16th GeV. It actually predicts that there is a standard model like Higgs with a mass below 130 GeV, and we found something that is consistent with that. And it provides clues to the dark side of the universe. And this is something we're trying to understand. So the dark side. Moving to the dark side. We know now that only about 5% of the energy in the universe is ordinary matter, okay, which is really surprising. About 27% is some form of dark matter that's not quite understood. We have ideas. And in fact, supersymmetry can happily predict this amount of dark matter. So that's one of the things we like about supersymmetry. The remaining 68% is dark energy, and we have a lot fewer good ideas about what that could be. It'll probably be taxed one day. Department of Dark Energy, I don't know. There are other possibilities, but supersymmetry is our favorite for explaining and solving this one problem that I mentioned, and also addressing the dark side. Okay, and I've mentioned all of the things that it can do. So what does it take to look for these particles, including the Higgs? Well, in our case, it takes a very large machine. So I show here the LHC accelerator complex in the Vallée Blanche near Geneva. And here you see the Alps. So it's quite a big machine. There are a couple of other machines that feed into it. But at least this gives you the scale of the machine that we're working with. And this is the experiment that I'm currently leading, the CMS experiment. Actually, this is a photograph of the experiment. That's made up of 350 million pixel photographs that had to be stitched together. But this is about 1/6 of the collaboration, maybe 1/7. So there are many, many people that are involved. It's a very complex machine, very complex experiment. We have over 4,000 scientists, including about 800 PhD students, many engineers, technicians from 41 countries, soon to be 42. And 190 institutions. And this shows how we distribute the data around the world, because believe it or not, there's so much data we can't store it at CERN. And so we ship it around the world, first to very large computing centers, and then to smaller ones, and then on to universities. And if we want to, we can actually get the data distributed worldwide within a few hours. But it's a big enterprise, and we've had to face some unprecedented challenges. This is what our events look like. When the beams cross, we have many protons colliding. And in fact, this has 50 simultaneous proton-proton interactions. And all of these charged particles from all of these high-energy interactions enter the experiment. And we have to somehow unravel all of that and get at the underlying physics. But the detectors are extraordinary. Here I show, maybe it's very beautiful to me. It may not be so beautiful to you, but this is an event where you see that we can reconstruct even very, very low momentum charged particles that are caught and just looping in the magnetic field. And this has never been possible before. And I wanted to mention this in particular because CMS, the particle tracker in this detector, CMS, UCSB, built more of this than any other institute in the world. All of that allowed us to make a major discovery that we announced on July 4th, as was mentioned by Pierre and Henry. And here I show the main points that were involved in the discovery. We saw an excess of events in the Higgs decaying to 2-photon channel in both the Atlas and CMS detectors. You can see the little bumps there. And we saw an excess of events also in the Higgs to 2Z detectors, channels, here and here, in both experiments. And in both cases, it was enough to reach a very high level of significance. And that was broadcast simultaneously in Europe and in Melbourne. And I like to say that it was 48 years, actually, since the idea was hatched. It was 20 years to design and build the experiments, 3 years to acquire the data, and a generation of work by thousands. And all they got for it was this lousy T-shirt. But actually, of course, it was more than that. It was a giant leap for science and a major breakthrough for us. And what was surprising to me was that it seemed to have captured the interest of the world. I really did not expect that. I don't think any of us quite expected that. So there were 17,000 articles written in 108 nations in 2 days. Okay, so moving on, I wanted to show you where we stand since then, because we've now analyzed all of the data. We have quite a bit more data than was shown at that time. And we have much nicer results now. So I'll go through those very quickly. So we have a much bigger signal now in the Higgs to 2Z case. And in fact, the probability that this could be due to just what we see in the data, but only background processes, is about 1 in 100 billion now. It's about 7 sigma. And it's about 92% of the strength that you'd expect for a standard model Higgs, but with a fairly large uncertainty. One of the important things that we've obtained, though, is the mass. In fact, that's not the correct value. I'll come back to that. We also looked in the photon channels, and where we had quite a strong signal originally, with more data, it actually became less strong, but it's still there. And it became much more consistent with the standard model. This I wanted to show you is just showing you the events being accumulated. You can see the dates here, okay? And it's very, very slow. You can see this Higgs signal growing very, very slowly. And I wanted to point this out to you because we move at kind of a glacial pace. You hear these discoveries and you think, many people think it was just one set of collisions. Poof, we got it. But it's very, very slow. And in fact, this small signal, which you'll see in the end, is only a few tens of events. I'll jump to the final picture. Maybe it's 30 events. That was what we dug out of around 1,000 trillion events, collisions. About 10 to the 15th collisions. One of the other important things we saw, this is the Z peak, the Z particle decaying to 2 taus. But when you subtract out all the expected backgrounds, we found an excess right at around 120 GeV. And this is the first really strong evidence that this particle decays to taus, which are fermions. And that's an important thing to see. We also measured the mass, and it was consistent, as I said, about 120. We looked for it to decay to Bs, and again, we see a little bit of an excess, not quite as significant, just a couple of sigma. But what's remarkable for those of you who have followed particle physics in any detail, this is a Z peak in BB bar. In a hadron collider, this is just phenomenal. We never thought this would be possible. We have an 8 sigma observation of the Z decaying to 2 Bs. And a 2 sigma, beginning to see a little bit of a hint of BB bar. And in fact, the strength that we see is completely consistent with what you'd expect for the standard model. So the last thing is we did look at much higher masses for a standard model like Higgs. We see nothing. We can set limits out to 1,000 GeV, which is more than 1,000 times the proton mass. We did see it in WW to 2 leptons and 2 neutrinos. You see this kind of I'm not explaining these plots, I'm sorry, but it's just you see an excess of this dashed line here. This black dashed line is what you'd expect if there was no signal at all. And this black line that you see up here, the solid black line, is what we actually observe. That's true in all cases. So we see something much above. That's what's expected. The red line shows what you'd expect if there were a Higgs with 125 GeV. Because there are neutrinos, there's no peak. So the signal is smeared out over many masses. But it's exactly what's expected. I wanted to mention this because the UCSB group was very strongly involved in that analysis. But if you put together all the properties, you find that the coupling strengths, how strong this new particle seems to be connected to the particles that we see it decay to or that are involved in its production, lie along this straight line once you take into account the differences in some of the scaling factors. And that's exactly what you'd expect if this were a standard model Higgs. As I mentioned, we have, with these decays to Bs and taus, we have some first evidence now for decays to fermions, which is very, very important. So, I didn't want to make that big of a deal out of it, but so summarizing these are sort of the main properties. The signal, the value 1, this is the strength of the signal over what you'd expect in the standard model. Along this dashed line is 1. This is what you'd expect if it was exactly on the standard model. And for all the channels we look at, you see we're somewhat, maybe a little bit low, but we're consistent. The mass turned out to be 125.7. We already have a very small uncertainty. And this turns out to be very profound. I'll come back to that in a moment. The other thing is its spin and parity. It turns out that it should be a spin zero particle with positive parity, meaning basically it sees itself the same as it with a mirror reflection. We've found that this is preferred over spin 2 or negative parity or spin 1 by very large factors. So all of this is consistent with a Higgs boson. And I just wanted to mention too that Atlas, our competition also sees something very consistent with the standard model. Now they tend to have a signal that's too high, and ours tends to be a little low. And if you put them together, it's even more consistent with the standard model. But you can see that the mass values that we measure are quite consistent with each other. So we're seeing a particle at 125.5, 6, or 7. Well, we showed most of this information for the first time in March, and that turned out to be a really big news week. First of all, we didn't expect this to make a lot of news, but it did, because we started for the first time to call it a Higgs boson. Before that, we were calling it a Higgs-like particle. But the same day, as you may remember, there was white smoke. And then we saw this. So, anyway, so where do we stand now? So it turns out to be really an interesting result for a number of reasons. There was a very nice talk given by a famous physicist named Guido Torelli, and I stole a few of his slides. He pointed out that this Higgs is very simple yet very unnatural. And I'll try to explain to you what I mean by that. And that the mass is a malicious, he combined the two experiments, he gets 125.6. Actually, the uncertainty is smaller than that. He says it's a malicious choice because this is where it is. And if you had the simplest, kind of most elegant form of supersymmetry, you'd want it to be down there. It's still okay up here, but this is not so easy. And for the standard model, you'd expect it to be up here, not down here. So it fell right where it causes the most trouble, actually. And it's creating a lot of desperation amongst many theorists that I know, which makes experimentalists very happy, actually. Because then they have to go and think and come up with something. And I think it's going to, in a small way, create a bit of a revolution. This is a little hard to explain, but the Higgs actually is a field that permeates the entire universe. So there's an energy potential associated with it. And the universe is sitting, we know, at the base of this potential, which looks like the bottom of a wine bottle. Okay? And the fact that there are many places for it to sit and it chooses one is actually very important. I won't go into why at the moment, but that's called spontaneous symmetry breaking. The question we have is the potential shallow like this? If it is, then quantum mechanically, the universe could tunnel out of it. And there could be another major phase transition in the universe, or it could be deep, really deep, and the universe is stable. Well, this is why it's a malicious choice. It turns out to be between the two. So the value that we get is right in a metastable region within the standard model context. So the universe, we believe, is metastable if the standard model is correct. It means it has a finite lifetime. It's a long lifetime, though. I wouldn't worry. So what comes next? Well, it's certainly been a great discovery, and we think there are more discoveries ahead. Here are some of my colleagues beginning to do work on some of the detector after we open it up. These discoveries, though, are probably not going to be like we had originally expected. Just like this boson that we found was not quite like was expected. But we can only study these things at the LHC. It's the only machine left on the planet that can produce Higgs or top quarks or Z's or W's for at least the next 15 years or so. All right, so the first thing we're going to try and do is try to really get to know this so simple Higgs. So we have to do very precise measurements. And in particular, we want to look at some of the couplings to fermions and vector bosons, other bosons. And as Guido said, it would be really astonishing if we went to extremely high accuracy and we found that they were exactly as expected from the standard model. Somewhere, something's got to give. And then there's this other issue. In his title, he said that the Higgs is so simple yet so unnatural this comes back to what I was telling you before about this natural balance. Okay? There's now a crisis because one thing we've seen is we've seen this Higgs, but we have not seen any evidence of supersymmetry in the simplest forms that should have jumped out at us. So people are starting to lose confidence that there is a natural solution, but as he points out, does nature really care about our concept of naturalness? You know, isn't nature natural by nature? Well, so we're wondering about this. And in fact, between the two experiments, what's pretty remarkable as well is that we already have over 500 publications, all of which break new ground in one way or another. But we have no evidence at all for supersymmetry, or anything new for that matter. And this was unexpected by at least some people. So many people thought we would see SUSY very early, that these very simple models would be true. And instead we've excluded supersymmetry partners to the quarks and gluons up to 1 TeV, that's more than 1,000 times the mass of the proton, and more than 1.8 TeV respectively. But have we? So is natural SUSY really ruled out? Almost. I say almost if you only consider these kind of Aristotelian forms of supersymmetry. For instance, we've almost always worked in what we call the constrained minimal supersymmetric model. And that is what I show here is this little green dot in a much bigger space of possible supersymmetry models. So it can really still be there. And we think it is there. And it may be at a low mass scale, but much more hidden than was originally thought. And this to me actually makes sense. I'm not sure I could explain to you why, but it seems to me to make sense. It could also be at a much higher mass scale and still be natural, which is not something people have really thought about recently, until recently. Uh-oh, it's not changing page. So, for example, what seems so simple might just be more complicated. We've always looked at the minimal supersymmetric model, but for example, the minimal supersymmetric model doesn't explain why supersymmetry is at the mass scale that it's at. You have to put that in by hand. If you go to the next to minimal supersymmetric model, you introduce another superfield, a singlet, you can actually set this mass scale for supersymmetry. And actually, I've always liked this model, but it turns out to be rather interesting because what happens now is when you look at the mass term for the Higgs, in addition to the basic term and the terms that come from, say, the top quark, there's a new term that comes in. And so what was a two-way balance that we were looking for before becomes a three-way balance. And so we haven't necessarily ruled anything out in this model. There's a lot more work to do. Now, supersymmetry, some people are starting to lose faith in, but I saw a really nice talk by Nima Arkani-Hamid in Edinburgh, where he sort of motivated particle physics based on very simple principles. And I can't reproduce it, but we've now found a spin 0 particle. We always knew about spin 1/2, spin 1 particles. You need spin 2 for gravity. The one thing that's missing from this picture is spin 3/2, and that appears in supersymmetry. But there are many, many reasons why supersymmetry is very, very attractive, and I think it's really there. There is this spectacular unification that I mentioned, and many other things that bring balance to the universe. He is also pointing out that the data seems to indicate that maybe all the scalars are very high, and the only thing that are low are fermions, and possibly just the electroweak GENOs, the particles that are partners to the electroweak bosons. And if that's the case, it's very hard to see them. It's very, very hard to see them. So we're in an interesting situation. We found the Higgs. It's not quite where anyone expected it to be. We haven't seen supersymmetry jumping out, so the simple models of supersymmetry are kind of looking tenuous at best. But there are many other manifestations of supersymmetry. And let me just say, I think the reason I think it's interesting, and a lot of experimentalists maybe were less surprised about this, was that it's kind of hard for us to understand why supersymmetry would have been jumping out at us as one of these points in a very complicated parameter space. Why would it be one point versus another? There are a couple ways you could go with this line of thinking. You could say, well, this is we happen to be in the universe that has this set of parameters. Or maybe there's something that drives the universe to be the way it is. And as experimentalists, we choose the latter because the former is not testable, for one thing. And all indications are that supersymmetry should be there, and it supports the universe in some way, but I think it is very hidden. And it's going to be hard to find, and I would be less surprised if it was much harder to find, and it turned up in a very subtle way. So we think now that we have a big job ahead of us, that experimentation is a very critical role now. We have to expand our capabilities. The detectors have to be upgraded to much greater capabilities. But in fact, there's very limited support for this in the US, for R&D in the US, which is too bad. Accelerators must also be upgraded, or new ones have to be built. Nations need to work together. Europe and Asia are actually moving forward with strong programs on this, but the US is not. And the US, in fact, plans to cut funding. So we're slowly falling out of this field. But the new physics is out there. There's no doubt about it. The question really is, do we have the tools to find it, and will we have the support we need? And that's probably the biggest concern we have now. The European Union, as I said, is very dedicated to this, and in fact chose the LHC as its top program till 2030. They're looking very far ahead. The program will be upgraded. We're here. The plan is to build a much higher luminosity version of the LHC, much more intense beams to look for rarer processes, and then increase the energy. And in fact, some people are starting to really think ahead. Let me jump ahead to building a new ring, which is much larger. It's 80 kilometers around, which is about the size of the SSC, as many of you know, that the US was building and cut. Okay, so what will we see next? Here's another picture of CMS. You're actually looking up from the floor. It's hard to tell. The answer is really, we really don't know. This is really pure exploration. But I would like to thank Pat and Joe Yzurdiaga for their support. Many, many thanks. The basic research in experimental science is really the cornerstone of the greatest scientific legacy of all time. I think there's never been anything like what has been developed in the last 100 years or so. But many of these areas, particularly in the US, are at risk. So this kind of support is extremely important and allows for a lot of creativity and a lot of continuation. And hopefully we can make some big discoveries with this in the future. So thank you very much.
Joe told me that he's certainly willing to take a few questions. Is there any questions left, or everything might be entirely clear? We'll go right to the reception. But if anyone has a question, please. There's a microphone coming your way.
And here too.
On one of your slides, you had a line about Aristotelian models. What did you mean by that?
Well, there was this belief that at one point people were very excited about a model. I think it was called M-Sugra. It's very similar to this constrained minimal supersymmetric model, where everything kind of unifies. All the masses at a very high energy scale, all the masses are the same. It's extremely beautiful. I meant in that sense. It was so beautiful that it didn't matter whether it was true, you know. And it was very strongly believed, and it was what everyone designed these experiments for, and all of the benchmarking was done with those experiments. It actually fell out of favor with the theoretical community long before it fell out of favor with the experimental community. But it gave the impression, and everyone had this impression, that it was the right direction, and it predicted things would just be jumping out of us. I mean, we were told we'd be discovering things in a few days. Now, we're going to go to a higher energy in a few years, and it could be that things jump out at us there. But a lot of experimentalists that I knew, at least, did not expect that, and we're not surprised that we didn't see something. Supersymmetry is not kind of jumping out at us all over the place in general in the cosmos. Maybe it's the dark matter and dark energy. But there's not a lot of other evidence for supersymmetry around. So my suspicion is that it's somewhere deep in the fabric, and we're going to have to dig it out.
One of your slides is a map of the world.
Yes. What am I
where
missing?
You put dots showing who participated. And I was a bit surprised to see that, according to you, Australia made no participation, which slightly surprised me. Is that an error, or is that really true?
That's really true. They have no participation in this experiment. They're in our competition. We have New Zealand, but some countries are only allowed to join one experiment because the cost it's hard to be effective for the cost. Yes.
Mine is a practical rather than theoretical question. You were saying that in the EU and Asia, they're supporting and have the project and have a long-term vision of it.
Yeah.
Where does that support come from? Is that governmental? Is it on the country basis? Is it academic? Is it business? Where has it come from in the United States and not coming from anymore?
Well, it's still there in the United States. It's going to be cut, at least for the LAC. And the support has been slowly declining for the last 20, 30 years in the U.S. But it comes from government funding. And that's true in all cases, actually. There's very little private contribution. There's a lot of university support, of course. Various groups help there. But CERN is interesting in the sense that there's a conglomeration of many countries that are combined. CERN has a dual mission, not only science, but to promote cooperation amongst European nations, now all world nations. And so they have a treaty. They're an international organization. There are treaties signed with many countries, and they maintain their funding, and it's very stable.
So I just say that this is actually broader than particle physics if you look at the investment the governments make in physical sciences. And in Europe, it's about twice as much as the U.S. per GDP or population. And it's in medical science, we're twice as much as the world. But in things like physical science, actually, Europe does invest more than we do.
Yep.
Is there any immediate or near-term military or defense significance to this nuclear work, similar to the Manhattan Project?
I can't tell you that. No, I don't. There are spin-offs that are relevant from our field, but not in the way you might be suspecting. There's no weaponry that we know of that can be developed from these things. But there are many people in the field that have been helping out with homeland security. Is that what it's called? I always want to say homeland defense, but it's homeland security, right? Developing neutron detectors, inexpensive neutron detectors for lining entrances to ports and things like this. So we help the Defense Department in that regard. But
actually, it went the other way around with the model from Russia.
Oh yeah, I didn't show that. We have. I don't have it in this, but part of our detector is built from shell casings from the old Russian Northern Fleet. Went the other way around. Mark.
Pat and Joe have been very generous supporters, as Henry mentioned, of student fellowships. And
Yes.
so I was wondering if you could say a few words about the role that students play at CMS.
The students, I mentioned we have almost 1,000 PhD students. And the students actually do a tremendous amount of the data analysis and operations. They do a lot of the key elements of the work. They have that. Well, they have the energy and the time. We work them to death, unfortunately, but they work. We don't do that. They're so driven. So our students have been excellent. All of our students, I think, from the UCSB group have gone on to really nice positions and have been extraordinary. It's if you were to actually take a snapshot of all the people who were closest to the discovery of the Higgs, they were probably all under 30. Those are the young people who were really the ones working around the clock on the data.
Actually, it will also be interesting to know where the students go. They do not just stay in physics, but many of them are in very different
That's
fields.
right. That's right. I don't know all the details, but they do go into many different fields. Some have gone into finance, I know.
Biomedical fields.
And a lot of different fields.
Any other questions?
You said you're good. Yeah, you're good. Hi, Kum.
I know that there is an art project that's set, and I wondered if you could say a little bit about learning physics through art and
Yes, we have an art. We've tried to make a connection to other areas at CERN, and so there is a connection to the arts. There's an arts, I think it's colliding arts program or something. Collision. I can't remember exactly the name. But in our experiment, we have some people that have developed. We do traveling art shows that are used to actually draw people in and discuss art, but also to discuss the physics and the science. And that's actually just taking off now. You attended one at CERN, right? Yeah, I think we saw some of it. There are many different activities going on.
So you said that right now the experiment, it's opened up and you're fixing things or upgrading things?
We're fixing many things. What was surprising in a positive way was that everything worked pretty well. The detectors worked at 90% level. It's not a trivial thing because there's 100 million channels of electronics. The collisions happen every 25 billionths of a second, so all 100 million channels have to be synchronized to a billionth of a second, which is not trivial. We take 40 million events per second. The mechanical tolerances are a few microns to a few hundred microns throughout this huge building-sized detector. And keeping it running 24 hours a day for 3 years is not trivial, but it held up. But there were many, many things that were bad, that had gone bad or potentially disastrous. We made it to the end of the run just sort of with our fingers crossed. And so we're fixing many, many things and upgrading many things and have a full program of work, actually 2 shifts a day, every day from now until end of 2014, basically.
So when will you start running again?
So we start running toward the end of 2014. We'll really be ramping up, and first data for physics will be in April of 2015. First results will be the summer of 2015 at a new energy. So maybe we'll still see Susie.
Any other questions for anyone? Otherwise, let's thank Joe again for working. I invite you all to a reception out in the courtyard, straight out here.